Okay, welcome back to this course on stereochemistry. Today we will be learning the nomenclature of molecules which can exhibit stereoisomerism. Okay. Like the nomenclature that you know for constitutional isomers, similarly there is a set of nomenclature system for molecules which can show stereoisomerism. But before we go on to the topic, let me just revisit what was stereoisomers and how many different types of stereoisomers are there. Stereoisomers are the molecules which have the same constitution, same connectivity. However, the arrangement of the groups in the space are different. Okay. In case of there is another in stereoisomers we have enantiomers on one side and diastereomers on the other side. Enantiomers are the ones which are mirror images, non superimposable mirror images of each other. Diastereomers are the ones which are not mirror images of each other, but they have the same molecular formula and same constitution. Okay. Now, in diastereomers, if there are more number of chiral centers, which are now modern terminology known as stereogenic centers are present, if there are more than one stereogenic centers present, and if between two molecules, two diastereomers, there is difference in the arrangement of the atoms in only one stereogenic center, then that is called epimer. That means, if you have now you know what are Fischer projections formula. So, if I draw the Fischer projection formula of a molecule which looks like this, and compare that with another molecule which looks like this one, now these are diastereomers because they are not mirror images of each other, but having the same constitution. So, they are diastereomers, but these diastereomers differ in the arrangement of groups around this carbon only, because the arrangement of groups around this carbon and that carbon remains the same. So, that will be called a special class which we have given the name epimers. So, epimers are diastereomers which differ in the arrangement of groups around one stereogenic center in a multi-stereogenic compound. Okay. There is another just to begin with, means in the beginning we should have actually said another one, which was that like isomers we have, if the molecules are same, if two molecules are same, then they are called homomers. Okay. Homomers, because we started with isomers, isomers are different molecules with same molecular formula, but then if two molecules have same molecular formula and if they are same, then they are called homomers. Of course, you can tell that why we have given we are bringing in this term homomers, but there are certain cases where this concept is required, because homomers are the molecules which are related by a C1 axis. That means, if a molecule, there are two molecules A and B, and if I rotate that molecule by 360 degree, I get B around an axis, that means it has got C1, then these two will be called homomers. So, homomers are basically molecules, they are same molecules which are related by a C1 symmetry. Just to bring in the concept of symmetry, we have this special class or special nomenclature for same molecules as homomers. Okay. Now, there is another third set which we did not another system which we have not spelled out yet, and those are called atrope isomers. So, we have diastereomers, amongst the diastereomers we have epimers, a special class where that they are differing in the configuration at only one stereogenic center. Atropisomers again a special class of molecules which are having again the same configuration, same constitution, but they are different. So, they are stereoisomers, but these stereoisomers are interconvertible by rotation. Suppose we have a system like this, two phenyl rings connected by a single bond, then because of the steric bulk of these A and B groups, these two rings take up an orthogonal orientation. And to convert, and while doing that they exhibit stereoisomerism. We will come back to this biphenyl, these are called biphenyls. We will come back to this biphenyl system later on, but right now just remember that this biphenyl system with different groups at these ortho positions, they can exhibit stereoisomerism. And to convert this one set into the other one, you have to rotate the biphenyl ring, one of the ring, and then by 180 degree to get to the other isomer. To make it clear, let me again just repeat that these type of systems they exhibit stereoisomerism. They can they actually, but in particular they show enantiomerism. So, they can exist in two pairs of enantiomers, but usually what happens in the normal case where we have stereogenic centers, to go from this to this molecule, you have to break one bond. When you exchange these two, when you interchange this position of these OH and H, you have to break a bond and then remake it. Here you do not have to break when you have the two that pair of enantiomers having this type of formula, you just rotate one ring by 180 degree to get to the other form. So, these are called a special class of enantiomerism, but they are known as atropisomers. So, atropisomers are stereoisomers which are interconvertible by rotation. Stereoisomers which are interconvertible by rotation. So, we will come back to this atropisomers issue later on. So, basically now we have in isomerism, we have the homomers which are basically same molecules, then we have constitutional isomers, then we have stereoisomers, and in the stereoisomers we have different classes, enantiomers and diastereomers. Enantiomers, there is another special class which is called atropisomers, which are interconvertible by rotation, and diastereomers you have a special class which are called epimers, where the difference is in the configuration or the arrangement of groups around in the space around a single stereogenic center. Epimers arise only in cases of molecules where there are multi stereogenic centers present. Okay. Now, let us go into this nomenclature system of stereoisomers. Okay. Now, how do we introduce the nomenclature system? Why it is required in case of stereoisomers? Now, we know that some molecules which are chiral, they have the ability to rotate the plane of plane polarized light. Now, if I ask someone to write the structure of plus lactic acid, okay, that means the lactic acid which rotates the plane of plane polarized light into the clockwise direction. So, if I ask someone to write plus lactic acid, what happens? You know the Fischer projection formula now that has been introduced. So, lactic acid is having a stereogenic center which is attached to a carboxy, which is attached to a OH, which is attached to a methyl, and which is attached to a hydrogen. Now, this molecule can exist as a pair of enantiomers. So, you can write the other enantiomer OH, COH, the mirror image of it. Now, if I ask which one is the plus lactic acid, it is not possible to know, because from Fisher projection formula, we cannot tell which one is plus or which one is minus. Okay. So, we have to, so in order to write the correct formula of plus lactic acid, if I know the absolute arrangement of the groups in space of plus lactic acid, then I have to have some way to describe its name, because simple saying plus lactic acid lands me into trouble that I can have two options. Okay. And for that reason, to describe the exact three dimensional arrangement of groups in space, we need a nomenclature system in case of stereoisomers. Okay. Now, so basically we have now the nomenclature system is basically for knowing for depicting the configuration of a molecule of a stereoisomer. Configuration, I wrote absolute, I will come back to this little later. First, let me explain what is meant by configuration. Configuration is the precise arrangement of groups around a stereogenic center. Around a stereogenic center, that is what is called configuration. Okay. Now, configuration, that means if I suppose this is one molecule, suppose this is lactic acid and suppose this is lactic acid, I have to assume something that okay, suppose this red is the carboxy, this is the methyl, this is the H and this is the OH. And if I know that this actually rotates the plane of plane polarization into the clockwise direction, then it becomes plus lactic acid. Now, the question is how to depict this molecule, how to in the three dimensional formula, that how to know that I have actually this one is plus or this one is minus, how to know that. For that a nomenclature system is required. Okay. I cannot say that you write it in such a way that the carboxy, that plus lactic acid is the one where the carboxy is at the top, the methyl is at the bottom, the OH is at the right, the H is at the left. That is the way to describe lactic acid, plus lactic acid. Okay. But that means it requires lot of sentences, lot of things, and if the molecule is more complicated, then you have to tell more and more that how to draw the structure of a chiral compound, okay, or a stereoisomer. So, to solve that issue, so absolute configuration is the precise arrangement of groups around a stereogenic center. Now, if you use the word precise, then it becomes absolute configuration. That means, you really know what is the, where are these blue, where is the blue group going, where is the green ball going, where is the red ball going, where is the white ball going. Okay. So, if you know that, that becomes absolute configuration of the molecule, and this is only obtained, this is very difficult to determine the absolute configuration. This is only obtained by X-ray crystallography. You can actually determine the absolute arrangement of the ligands in the three dimensional space. Okay. Now, there is another term which is called relative configuration. So, like absolute configuration, we have relative configuration. Now, what is relative configuration? Relative configuration is, if I cannot, if I have a molecule which a chiral molecule, I want to determine its configuration, but I do not have a crystal, I cannot do a crystallography. Then what is my option? My option is that if I can synthesize this molecule starting from a compound which has got known configuration. So, I convert this slowly into by different steps and then make the molecule that is in my right hand. Then, although I did not directly determine the absolute configuration of this molecule, but what I am now able to say that this has got a similar configuration or a different configuration, that depends on the sequence of steps in between, Suppose it is the similar configuration like what it has, then this configuration becomes a relative configuration, because you are not directly determining the configuration of this. It is determined starting from a molecule of known configuration, or the other way you can actually convert this one into a molecule of known configuration. So, then the configuration of this becomes relative configuration, because its configuration is determined in relation to the configuration of this. So, if you know the configuration of the molecule in the left hand, then you know the configuration of the molecule in the right hand. Okay. So, that is the relative configuration. There is another type of relative configuration, and that is in molecules where there are more than one stereogenic center is present. Like say I draw the structure of optically active tartaric acid. So, this is the structure of optically active tartaric acid. Okay. Now, optically active tartaric acid can be plus or can be minus, dextro or levo. Again, if I suppose we think that this is, it may not be true, but suppose for the time being let us say that this is plus tartaric acid, this is the plus one, the dextro form. Okay. But I do not know the exact configuration of these carbons. What I know is that if I draw it in the Fischer projection, the two wedges actually are on the opposite side. Okay. So, if I say that plus tartaric acid is that molecule where the two wedges are on the opposite side, then how many structures you can draw? You can see, this is one possibility. If I only say that the wedges are on the opposite sides, then you have to draw the other structure also. If plus tartaric acid is described only by that fact that in the Fischer projection formula, where you put the carboxy in the right perspective, because the main chain in the Fischer projection is kept in the along the vertical line, and then if I say what is plus tartaric acid, the one where there are two wedges are on the opposite sides. Okay. But still you cannot write one unified formula, you have to write both these two. Okay. But this, what I am saying, that the two wedges are on the opposite side, that means if I can determine the configuration of this, then I can determine the configuration of this, because I already know that they are on the opposite side. Okay. So, here basically what we are talking about is the relation between the two configurations. So, relative configuration, one is that if you have a known configuration of a molecule which is determined by X-ray, and then if you can convert it to another molecule, then this molecule's relative configuration you know, because you know the configuration of your starting material. That is one type of relative configuration. The other is that in a multi-stereogenic center, the relation between the two configurations of the stereogenic centers is called the relative configuration. So, there are nomenclature systems which can, because there is another tartaric acid which is where the two wedges are on the same side. Okay. So, if I ask you to now differentiate between plus minus or this one, that tartaric acid which is the mesotartaric acid, I have to have some nomenclature system. Okay. Mesotartaric acid is easier one, because you know that it has to have a plane of symmetry, it is easier to write, but if the groups are different here, then that plane of symmetry is gone. Okay. But if I want to tell a student to write the structure of a compound, where the two wedges are on the both sides, then he has to write another compound, unless it is a meso. So, that is the other compound. So, that means what I am saying, I am telling the configuration of one in relation to the other. Okay. That is relative configuration. And today we will discuss the nomenclature system of both the absolute and the relative configuration. We will start with the absolute configuration. Okay. Now, the whole story started when Emil Fischer, he was trying to determine the structure of the carbohydrate, and the one he tried to do was the naturally occurring plus glucose. Okay. So, he wanted to know what is the absolute configuration of plus glucose, and ultimately he ended up with the possibility of two structures for plus glucose. One is this one, this is a big molecule because this is a carbohydrate, this is called aldohexoses. So, he ended up that plus glucose is either this one or plus glucose is the mirror image of this. That means, he could not get a crystal of plus glucose to determine the absolute configuration. So, one of these is plus glucose, and he assumed that the plus glucose is the one, is the right hand one, because he assumed that in plus glucose there are, say in this molecule how many stereogenic centers are there. This is one, this is another one, this is the third one, this is the fourth one. There are 4 stereogenic groups. Okay. So, he assumed that the last stereogenic center, the weight is on the right side. Now, he knew the relative configuration. See, he knew that the first weight, if it is on the right side, then the second weight will be on the left side, and if it is on the left side, third weight will be on the right side, and the fourth weight will be on the right side. So, that means, he knew the relative stereochemistry, the relative configuration, but to know the absolute configuration at that time he could not have the extra crystallographic structure. So, he assumed that plus glucose, the last, that means this one. So, if you number it 1, 2, 3, 4, 5, 6. So, the C5 carbon, which is the last stereogenic center, and that in the IUPAC nomenclature system, in that the weight is on the right side, and he called this as D plus glucose, D plus glucose. Okay. So, that is your D plus glucose, and from this a nomenclature system ultimately came out, and that is, of course, that is the older nomenclature system, that is called DL nomenclature system. What is DL nomenclature system? DL nomenclature system is that if you have a molecule, it again started from this concept, that if you have a molecule like this, which is say glyceraldehyde. So, if you have glyceraldehyde and write it in the proper Fischer projection formula, proper means proper in the sense what is required for naming it according to D and L, because Fischer projection formula you can place the 4 ligands in at your will. You can put the OH here, the CH2OH there, but if you are trying to determine the absolute configuration, then you write it in such a way that the most oxidized group is at the top. First of all, the carbon chain has to be in the vertical axis, and then keep the more oxidized carbon at the top and the less oxidized carbon at the bottom. There is another way of saying this, that if you want to name it in the IUPAC nomenclature system, this belongs to number 1 and this is the 2 and this is the 3. So, either you say that I put the most oxidized group at the top and then the less oxidized group at the bottom. Then if I see that the heteroatom, that means the weight is on the right side, that will be called D configuration, and the opposite one will be called the L configuration. So, this is D glyceraldehyde and this is L glyceraldehyde. Remember, this is not minus, this is just a hyphen, D glyceraldehyde, because from the structure that is given, it is not possible to predict what will be the sign of rotation. Sign of rotation is entirely an experimental thing. From the structure you cannot tell what will be the sign of rotation of this compound. So, what we can say only that this is D-glyceraldehyde and this is L-glyceraldehyde. Okay. So, so this was the initial nomenclature system. That means, if you have, it was extended to other systems, not only which they tried to, there was a scientist Rozanov, he gave some rules. He said that if you have a compound like this R 1 C H X and R 2, and if I want to write, suppose I ask you to write the L configuration of this, then how do you write it? First you decide amongst the R 1 and R 2 which one is more oxidized. Suppose R 1 is the more oxidized group here, or R 1 contains the number 1 carbon in the IUPAC nomenclature system. Okay. Because in IUPAC nomenclature, that is the rule, that oxidized carbon given the number 1 group. So, R 1 will be at the top, R 2 being less oxidized at the bottom. So, if I am asked to write the L configuration of this, then X is here, H is there. So, this is the molecule in L configuration. Okay. So, basically this DL nomenclature system is applicable for systems like this. That means, 2 alkyl groups, a heteroatom and H. This DL nomenclature system is still being used in carbohydrate chemistry as well as in amino acid chemistry. In amino acids, we know that amino acids have a carboxy group, an alkyl group, and then an NH2 and a H. So, according to DL nomenclature, this has been written in correct format because the most oxidized group at the top, and then you are seeing the heteroatom to the left. So, that becomes L, and this is the configuration of natural the amino acids which makes the proteins in our body. Okay. So, they have the L configuration. However, this method of absolute configuration is not universal, is not very general. Why? Because suppose you do not, in many cases you may not have any heteroatom, you may have another R 3 and R 4, then what are you going to do? There is no heteroatom. So, DL nomenclature will not be applicable here. Similarly, if you have 2 heteroatoms now, X and Y, so this is not applicable here, dual nomenclature. Again, if you have 2 heteroatoms, you cannot really tell which one is which, because there is no such rule which heteroatom has to be placed on the right or which heteroatom has to be considered to the left. Okay. So, DL nomenclature system is not universal, it has a historical story, and then Rozanov tried to extend it further to name the absolute configuration of compounds which have, again I tell you, it is applicable for compounds which have got R 1, R 2, X and hydrogen. For that system it is applicable, otherwise for many other systems it fails. So, the communists, the community felt the need for introduction of another methodology, which is applicable to all systems, and that is what is called RS nomenclature. Okay, RS nomenclature, and this RS nomenclature is also known as CIP nomenclature system, because this was proposed by 3 scientists, Kahn, Ingold and Prelog. Okay. So, these 3 scientists met with each other and then proposed a very beautiful, very nice and a very simplified way to give absolute configuration nomenclature to compounds which exhibit stereoisomerism. Okay. Thank you.